Yeah, I guess we are recording. Um, Hello all, and welcome to the first live session of your course, Intro to Machine Learning. So my name is Raj, and I'm a student at IIC here, PhD student at IIC here. And I'm one of the three PMRF TAs. That is basically we are a bit different from the course TAs. That is, we will interact with you once a week, each of us, and help any if you have any doubts or something to get clarified in a live session format. Um, if you notice, there is a Q&A section for this particular, Teams chat. You are, free to post your questions there, and we others and me included can answer your questions there. But mind you that this is just for this particular, Teams, method. So only I will have access to it. The usual Google group discussion group that is there, that's accessible to all, so you can feel free to ask the question there also. And I see that group regularly, so in case there is a question that you specifically want to ask me, just I guess there's a way to mention someone to do that, so you can go ahead and do that. um, so because it's the first session, so I just wanted to understand if you have any doubts that you have till now, going through the course material till now. So if any doubts, if you have, you can, raise your hand one by one. We can, tackle them individually, or if you want to do something like a more general sort of a discussion, then let me know. We can do that also. All right. So we have some this one. Um, right. So I'm not sure. Green and brown solutions. Yeah. Please go ahead.
Sorry, I unmute. Yeah. My name is Arijit Datta. I just joined this course.
Sure.
Uh, Thing is that for the course material, particularly that inductive bias, that part just not, I mean, gone over the
Yeah.
head.
Okay.
I am, yeah. So maybe a little bit throwing light into it will be better for the perception wise, because if the previous two chapter is okay,
Mm.
clear, but this one inductive bias and that part is we don't understand
Got it. Got it.
because I'm not from the IT background. I'm telling you
Right.
that.
Yeah. Actually, thank you for the reminder. So, I guess many of you have very different backgrounds coming in. Some of you want to use the course to, go through GATE. Some of you have ideas going into industry, for example. Some of you want to shift your, line of work, or some of you want to use ML in your line of work, and so on. So, feel free to, ask questions regarding those things also. With whatever little experience we have, we can probably guide you towards the right solutions in that space also, if you want. So yeah, coming to the inductive bias thing. Um, right. So, okay. So first of all, the idea is that we have this idea of hypothesis space, right? That is basically we have a space of all possible functions which we want to explore and find the best function which can explain our data that we have, right? Now, for example, let's say if I have like a hypothesis space of H. Now the thing is, H as a space is a very large space as such, right? So then what do we do is that to be able to at least find some solution, we place some restriction on the function that we want, right? So one such restriction could be the form of the function that we want, right? So that is basically saying, I want to look at only linear functions. Now, for example, let me give you an example here. So I'm not sure if this is working well. So for example, let's say I have a regression problem, f of x, and it's of this form, right? Um, I hope this is clear. It's the first time using a board and something like that. So the idea here is, for example, let's say I have a regression problem that is basically I have a set of features and I want to predict a continuous value out of it. If I choose my functional form to be this, right? That is, I will only look at functions which are linear in X, right? Now that poses a restriction on the sort of functions that you can hopefully find as a solution to your problem. Now this is called inductive bias, right? Because you're somehow you're not looking at all possible space of functions, but you're choosing one particular sort of a space of function, which is linear functions, and trying to find the best solution in that particular space, right? So the space of all functions which satisfy this particular relation is a smaller set of, let's say, a larger set of hypothesis space. So we have chosen a smaller space and we want to find the best in that particular space. This is called as inductive bias, basically choosing some sort of a function, some sort of what you can say, like a restriction on the form of the function that we want to discover from our data, right? So this is inductive bias. Hopefully this is clear. Any more doubts? You can go ahead and please go ahead and ask.
I just want to, I'm Sam Arijdatta speaking. So this one is mainly what you want to say that there may be different functions, that is a linear type or non-linear, polynomial, different kinds. So who is attempting the problem will try to understand what it could be, and then it is choosing that type of functions which can possibly give the right answer. Or
Right.
that is a, yeah. So that is the inductive bias in the we are choosing it, right? That means, so it may be instead of linear function, it will be a different functions also, logarithmic functions or something like that. That you mean, right?
Exactly. Right. Yes. So what's happening? For example, let's say if the data actually is of this form. For example, let's say it's something like a quadratic. So at the end, what ends up happening is you will only be able to find functions which are linear because it's a linear function in X, right? So whichever values of, let's say, beta naught and beta one, for example, give you the best sort of a estimate on your test data or a validation data, for example, right? That you will end up choosing. But actually the thing is that you have your data to be a quadratic form. Now, just because you didn't think of trying a quadratic function, or you didn't want a quadratic function, you ended up getting this answer. So this is what we mean by inductive bias. So somebody asked in chat, how do we get bias into here? Yeah. So I mean, yeah, it's so I would say, like, hold off a bit on the math part until there. We'll get to there, and there it'll become clear why, like, why is it termed bias and stuff like that. So one very crude sort of I can tell you imagination. I mean, here is that. In a way you're biasing your search space itself, right? You're saying, okay, I don't want anything else. Rather than looking at the actual relation, you're saying, okay, I will look at only one particular side of it. So that's, in a way, I will say, a bias. But hold off until the math. I think we'll come there and we'll get to the in more clarity.
Okay, this is Lakshmi Narayana, the one who asked this question regarding the bias. Am I audible to you?
Yes, go ahead.
What I meant by in terms of asking how we get the bias is it because of we are selecting and approximating the reality with the mathematical function that we are choosing? Is that because we are calling it as a bias?
Yes, precisely. That's the reason, right? Because
Okay,
we don't know the actual form. We don't know the actual
right.
realistic form. So what
Hmm.
we have done is we have said, okay, we will assume a form and we'll go ahead.
Right,
But that form may not be right. So hence
right.
the part of bias here, because we have chosen
Okay,
a form that we are sort of whatever comfortable with or want, for example.
okay. Thank you.
Yeah. Um,
Yeah.
next, I guess. So you need not have your videos on. I mean, just in case, because people can have issues with their internet issues. So green. I'm sorry, I forgot your name. So if you have any other questions, you continue. Otherwise, we'll go to the next person.
Sir, I have a question. Myself, Subhajit Bhattacharya.
I'm sorry, Subhajit. Yeah, go ahead.
Yeah. I'm Subhajit Bhattacharya, mechanical engineering background. So I
Sure.
have a question on validation and testing.
Okay.
So why validation is different from testing, or validation set is taken as different from testing?
Right. Okay. So this actually leads to a more philosophical sort of question. So if you think about it, what are we trying to do in machine learning, right? We are trying to build we're trying to learn patterns from the data, which is useful, which hopefully helps you uncover the truth about the data, right? Now the thing is, once you get your function, once you learn whatever function that you're supposed to learn, then you want to use that function somewhere, right? As ma'am spoke in her videos, that yeah. So as ma'am spoke, like, so we actually get a program as the output of a machine learning algorithm, right? So we want to use a program somewhere, right? So basically the idea is that and we don't know what sort of data is going to come at that time when you're using the program for your whatever work that you wanted to use for. So that is the idea of test data. So what you do is you say, okay, from all the data that I have till now, I'll choose some amount of data as test data, thinking that this data doesn't exist at all in the first place, right? Because this mimics the real world scenario of any data which can come in the future. So to mimic that sort of a learning process, we say, okay, I will not consider this at all. Now, why do you need a validation data? Because now, since that data is lost, you still want to understand how good is it in trying to generalize to unseen data, right? So that part is that role is played by this validation set. Now, validation set, there's one another use case is basically tuning the hyperparameters. Now, we'll get to this in the probably in the next or the next to next week lectures. Um, each of these functions that we end up choosing, your hypothesis space that we end up choosing, they have some parameters which cannot be learned from the data itself. So what we do is we use validation data to be able to come to a good estimate of what these other parameters could be. They also called as hyperparameters, right? And that is then used to evaluate on the test data. So the test data is basically used only once in your whole ML pipeline to understand what is the final output. That's it. So that is the reason why we need two separate things. One is validation, one is test data. Yeah, Shubhaji,
Okay,
so
thank you, sir.
is it? Yeah, okay, fine. Yeah.
Sir, good afternoon.
Sir, yeah.
Yeah, myself, Dr. Swayam Sarkar. I am from the chemical engineering background, and I
Yeah.
have attended Professor J. Mighty during my PhD coursework. Okay,
Sorry,
on
Professor.
related to multi. I have attended Professor J. Mighty's course in ISC department, multivariate statistical modeling. Okay,
Okay.
where we had been knowing him, right?
I'm sorry. You'll have to be a bit clear. The voice is not coming up clearly.
Okay, my question is, I have an optimization problem. Can you
Right.
hear me?
Yes, go ahead.
Yeah, I have an optimization problem where my objective function is stated. Let's say my objective function is to minimize some square error
Some squared error. Right.
of
Okay.
a data set.
Right.
Okay, now tell me, I fail to understand one thing. Like when you say hypothesis, capital H is a set of hypotheses, right? So small h is a subset of capital H.
Right. Yeah.
Now, when there are this feature 2x2 matrix, sorry, 4x4 matrix, what Professor Sudeshma Sarkar had mentioned in her videos. Now, she said that it should be 2 to the power 4, that is 16 is the total number of data sets, or total number of data,
Okay.
right?
Which you're talking about this one, by the way?
I'm talking about the second lecture where Madam Sarkar mentioned that the number of hypotheses will be 2 to the power 16. May I know how can that be calculated?
So I can answer this. Like it's like 2 to the power 4 is the number of instances. Now, if you take a Boolean function, each instance can be put in say positive side or the negative side. So 16 means each 16 you can take it as a bit, digital bit 10. So 2 to the power 16 instances. So you can have total 2 to the power 16 Boolean functions basically. So if there are say 4 feature variable which are Boolean variables, there are total the sample space will be 2 to the power 4, that is 16 instances. Now there can be
Total
sample
16,
space of instances is 16, 2 to the power 4. Okay, and now these 16 points we can take up one function in such a way that you can these 16 points you can put it on its right hand side or the left hand side. Okay, so it will become, you can take how many such functions, you can create how many such functions. Since there are 16 points, you can create 2 to the power 16. That's the number of Boolean functions possible, and that is the capital H.
Okay, out of which, how we will calculate small h?
Now small h will come according to, like, whatever, if you are taking some bias, then out of that 16, 2 to the power 16, we will reduce that set. Okay, we will take a small set. That will come from a particular optimization problem. Means if it means according to your samples point in that n-dimensional space, it will come from that, like how you are restricting your capital H to your small h. See that?
Okay, okay. And afterwards, in the fourth lecture, Madam Shortkar has mentioned that by using this constraint, we can, some accuracy or some error, if we calculate, then we can lead to the exact age. Am I correct in my understanding?
Can you repeat again your words?
Small h, let us assume small h is now calculated. Let's say out of 2 to the power 16, we now get small h as, let's say, 8 points. Okay.
8 points, no, take 8 functions. It has 8 functions.
I'm sorry.
16 points.
8 functions.
8, mind it, it's 8 Boolean functions. Okay, only
Yeah,
right hand side. Yeah. Okay.
Yeah. Okay. So we get this 8 Boolean functions applying some bias in terms of constraints.
Yeah.
Or
you can take it like that. You can take it like that. If you're reducing your sample function space, basically, theoretically, say if you're taking instead of non-linear, you are going to linear, your small h is becoming a subset of capital H. That's the thing.
Okay, okay. So basically, what I understand now is that small h will only come when we apply some constraints or
Correct.
some bias.
Yes. Correct.
Oh, okay. And this small h has nothing to do with the objective function that we take.
Objective function is the reality that will correctly divide your instances into that Boolean functions, say right hand side, left. We are trying to approximate that. Okay.
Okay. Okay.
And
Okay,
by
thank
taking
you.
a wrong h, small h, then you can, it creates errors basically. It creates errors. Accuracy will reduce.
I see. Okay. Okay, thank you.
Thanks,
Hello,
Abhi.
sir.
Yeah, go ahead. Abhi.
Hi, I am Sudipto and I am a student in data science program. Okay, and I just wanted to ask you one thing, that this is going to be means a problem solving, that the lectures that were that was yes, the previous lectures were there, and we are going to discuss those things, right? Or you are going to show some practical examples of the coding or something like that.
So coding examples, so based on how the lectures go, if they are, then we will do that, but otherwise mostly we will not. I mean, see, if you want, coding examples, we can do that also. So just go ahead and mention it on the discussion group. We'll do that, not a problem. So it's again, this is meant for mainly, supplement whatever is being taught in the lectures. So if you feel that's a valuable add, we can do that also, not a problem.
Okay, thank you.
Yeah. Aman, you had something to ask? Okay. Yeah, so we have okay. Can you tell about confusion matrix? Yeah. So what about confusion matrix? So what was confusing about confusion matrix? Who asked this question? Sankari. You can type it also if your audio has an issue or something. So, so in general, what confusion matrix basically means is that you're trying to look at how good your true how good your predictions are with respect to your true labels, for example. So let's say for example, if this so for example, let's say you have uh, you have a test set, or let's say a validation set, right? Which has, for example, let's say 10 positive examples and 10 negative examples, and your algorithm which you had which you have learned or whatever, right? Your ML program that is now supposed to tell you whether a particular sample was positive or negative, right? So then what you do is you build a very simple count matrix sort of a thing, right? And then say, let's say if this is a ground truth or whatever, and this is a prediction. I hope this is visible. So let's say positive, negative, and positive and negative, right? So so now the idea is how many of the ground truth positive examples did your prediction also tell it as positive, right? So for example, let's say the total are, let's say 10 and 10. If this is, let's say 2, this becomes 8. And let's say, for example, this is, let's say 2 again, let's say 8, right? So 20, and you can just look at the total sums, right? So now if you see, so what's happening here is that your prediction module, what it seems to be doing is it's giving most of the examples this negative prediction, right? Ideally, it should have given this. I should have had here 10 and 10 here, but rather it's somehow sort of, let's say, biased in the thought of saying that okay, I will just keep on giving negative prediction as the output, right, for whatever reason, right? So this is a confusion matrix. Now from this we derive useful information thing. One thing is called precision, other is called as recall. So precision and recall, right? So what recall is basically is among the actual true, actual positive examples, how many could the model tell, positive, right? So in this here, for example, actually I have 10 positive examples, but the model could tell only 2 of them as positive, right? So the recall becomes 0.2, it's 20%. And precision is basically among all the outputs that the model has told positive, how many are actually positive, right? So among the model that is among all the predictions that the model has made as positive, that is 4. Out of 4, 2 are actually positive. So this is 2 by 4. That's half. That's 50%, right? So ideally, what we want your precision and recall both to be very high, right? For a classification algorithm to be able to do to actually say that okay, it is doing well, right? And then again, this is for a binary classification problem. So when you go for multi-class classification, that's a different. There are different variations to this problem, and how do we look at, this idea? Yeah. So that's about confusion matrix. Any extra question? Any other doubts on this? You can continue. Um, okay, good enough. So let's. Okay, next we have this question on bias and variance, right? So. Yeah, let me just take this up, Veena, and then I'll get back to you. So yeah, so bias and variance. So first thing is that okay, so we'll come to a mathematical treatment of this two terms, bias and variance, much more strongly going forward. But okay, so let's say your true function is, let's say, f, right? So this is y equals to f of x, for example, right? This is your y equal to f of x, and now you have chosen some hypothesis space, right? Using some induction bias, you assume some form of f, right? Let's say I'll call it f hat, right? And you will run this on this x, and you will get y hat, right? So now there are two possible problems that can exist in this approximation that is there. So one is that the approximation may not be able to even learn the basic patterns in the data, right? So that is termed as bias, and variance is basically from the fact that you just because of the fact that you don't have enough samples in your data to be to learn this f more. So basically seeing that, okay, how good is f hat compared to f, you don't have enough data to even learn the f properly, right? That creeps into your this thing called as variance. So again, it is a very superficial way of explaining this. So when we get into the math, I think it'll become bit more clear. And why we and why we use in the sense is because we want to see how good can we get to a particular function, the true function compared to your approximation. So that's the thought process of using this bias and variance terms. And we want to be able to understand how good it is or not, right? So that's the reasoning. Yeah, that's all I can tell for now. We'll get into the math, and then it'll become more clear how samples affect this variance and stuff like that. Yeah. So you can close your videos if that's Sudhakar ready, for example. You can close your videos, not a problem. Subhajit, you have a question?
No, I questioned that validation and testing. You have answered. I got it.
Okay, good enough. You can lower your hand then. Okay, is Python programming required to clear the course? I'll have to check the upcoming, schedules. If there is, we'll make it clear to you guys. Not a problem. Over the discussion forum. Yeah. So I'll make a note of it. Mostly it is not, because it's supposed to be a theoretical course. Otherwise, we'll make it clear on the channel. Recording, yes, it will be it's being recorded and will be posted also on you get a link through the NPTEL announcement mails. Yeah.
Excuse me, sir.
Yeah, go ahead. How is it? Go ahead.
Can you give some explanations about training set, test sets, validation set?
Okay. Fine. So so let's say, for example, again, this is a very simple problem, famous problem of machine learning. Let's say you want to find out whether an image that is given to you is of a cat or a dog, right? Very simple sort of a problem statement. So you have an image, right? And you need to classify it as either cat or a dog. And let's say I'll give you, for now, I'll tell you that, okay, no cheating. It'll either always be a cat or a dog, and one cat, one dog, but you tell me which it is, cat or a dog, right? So now what we'll do is, so this is a problem that we have. We have an image. We want to classify it into two classes, that is cat or a dog. Now, to learn this mapping, that is to know, okay, how do I, how do I build a program which can do that for me? So for that, what we do is we say, okay, I will use some existing examples that are there. For example, let's say there are some people who have already seen a particular images and telling you, okay, this is a cat, this is a dog. So what I will do now is I have this labeled set with me, right? Labeled set with me, which has an image and the class that it belongs to, right? Whether it is a cat or a dog. So now I use this particular labeled set to learn the function which can go from this image space and tell me, okay, whether it is a cat or a dog. So this is called a training set, because we're using this set to learn the function which can map from this image space to this classification space, right? Now it's possible for the model to not learn anything useful. Now this is exactly, for example, when let's say when you have to give an exam, there are two ways to get a high score in the exam, right? One is you memorize everything in your textbook. That's one thing, but you haven't understood anything from the textbook. Or the other way is you learn everything and understand everything, right? So the model, so because we are the way we are training the model is we're saying, okay, you need to do well in the training set, right? So the model can cheat and tell and can just memorize what is there in these examples to give you the right answer, right? So you might be fooled into thinking that the model has learned the right function, the right mapping between this particular thing, right? So hence what we do is we have another set called the validation set, right? Validation set is basically used to understand how as a model generalized in terms of its learning process. So we test the model on this validation set, something which the model has never seen before, right? Only then can you understand between two students who have actually learned the way of doing things or memorized, right? So in that way, we have this validation set which we will use to check whether the model has learned the right mapping or not, right? The test set is basically something that doesn't even exist yet, right? So now by learning and by checking, okay, the model has learned properly, it's doing well and all of that. Then when you want to use this particular program that that the ML model has given you, it's at the end a program, right? That program is, you will then use it in your whatever application you want. For example, let's say you have a web page that you own, and for fun you want to put there up and saying, okay, give me an image, I'll tell you whether it's cat or a dog. That's the test set, something that doesn't exist but will come as an input to your ML model, and you're supposed to give an output for it, right? This is the conceptually the what training set, validation set, and test set mean. So training set is basically used to learn the function. Validation set is used to understand whether the function is good enough or not, right? Has it memorized or has it learned the right patterns to give me the right answer or not? And test set is something that comes at the later end. So once the model is trained, once the model has all the learned patterns, we then look at the test output. Yeah. So Gandhimati, is this fine? Any follow-up
Yes,
question?
sir, it's clear. At the same time, we have some ratio of having the test set, validation set, and the training set, no?
Right.
Generally, what is a basic ratio? Maximum we used to have 75-25% or 80-20 in that combination. Is there is any constraint to have in this ratio or any ratio we can have?
So yes, theoretically, I mean, there is no guaranteed or uh, a rule that exists that you must use so and so ratio. It is just something that it's more of a thumb rule, more of a like a word of mouth in some sense, right? Which seems to work for people. Now, so generally what people use is people can use either 75 15 50, 70 15 15, right? So 70% training, 15% validation, 15% testing, or you can have 80 10 10. That's generally what we do. Now ideally you wouldn't want to have a very small training set, obviously, because you want to learn the patterns, so you want to be able to use as much as your data possible to learn the function, right? So you will not use like a 20 80 10 sort of a split, 10 80 10, sorry, right? So rather you want to give a large chunk of the data to training, and almost equal chunk to your validation and testing, because we want to simulate the real behavior in your ML workflow also. So we usually try to give the similar ratio for validation and testing.
Okay, sir. Thank you.
Right. So yeah, how machine learning is different from artificial intelligence? Okay, so AI is a much broader term for ML. ML is one part of AI, I would say, and AI has something like a knowledge representation. Then there's a whole other thing called search that exists, right? What is optimal way of searching in different space and all of that. So now it seems like the lines are blurring a bit, but yeah, AI is a much broader term for ML. That's how I would put it. What book should I follow? Again, I'm not really sure about the book which you should follow. Post it on the discussion group, and probably the course TAs might be able to help you out there better. Then after validation, testing has to be done. Yes, exactly. So hence what we do is, let's say you have a lot of data. I mean, whatever data you have, you split between your training, validation, and testing. Training you will use to learn the function. Validation you will use to understand how well is it able to generalize. Then once you're then you will choose the best model based on what has which has the best generalization ability, right? After that you will use a training set to get the training accuracy or training loss or whatever. That's it. So training data, test data you will use only once, right? So you will use the test data to get your test accuracy or test loss or whatever, and that's it. That's the number that you have to report or use in your whatever experiments that you want to do, right? So after validation you go ahead and do testing. What's the minimum number of data set to ensure more than 90% accuracy? Although subjective question, I know what I'm asking. What want to know average data set number where we can get for practice? The question, you answered your question actually. That is a subjective question. It depends on the data set. It depends upon how noisy the data set is. A lot of factors, and there is no mathematical there's we don't even have an inkling of what is the right number. Okay.
Sir,
I'm sorry.
excuse me, sir. Sir, what happens if we increase the training error? I mean, a sample, sorry. See, initially we have taken 70, 30, and based on 70, we have done, our model is ready. Once the model is ready, instead of doing validation test, we again decided to increase the sample. I mean, the training samples. So what happens to actually training error when I increase the sample to 10%? Will it increase? Will it decrease?
Um, so um, So let's say if your model has learned the right function that exists, right? For example, let's say somehow miraculously you could, your previous training set that you use, the 70% one, you got some results, and let's say hopefully the model has learned the right function, the right mapping, right? So then increasing your training set data is not going to help you at all, right? Because it's already learned. So there's no point training it anymore because it has learned the right mapping. Now, and it doesn't happen generally. So ideally what happens is when you increase your training data, your training error at the end of the day will reduce. Okay, because your the metric for evaluation or the way you will update your ML model, all depends upon the training data. So what will end up happening is you will eventually be able to do better on the training set, but that may not guarantee that you will do well on the validation set or the test set. That guarantee is never there. Even with any ratio you use, you will never get that guarantee for any ML algorithm, generally speaking. Because at the end of the day, what the claim we are making is that the whatever the function exists in the real world, we don't know that function. We're trying to approximate it in some way. So the approximation may either be very good or very off. There's no way to know that.
Okay, thank you, sir.
Yeah.
Sir, one more question.
Yes,
I'm
Gandhi.
Gandhi. You said there is we could able to find the error rate after evaluation. In which basis we can identify the error rate after we have segregated the training set, validation set, and we used to get some result based on our given data set. Actually, we are segregating the given data set into three parts. Is it so? No, training,
Yes.
validation, and testing.
Yeah.
Based on our actual input values, we may get some possible output. And if it is not right, as you said, the test sets can be any value which is not expected to the learning level. In that cases, how will we get the error rate? How can we know any proper notification of that error, or
So basically what you do is
any representations for the error rate, sir?
So by error rate, I'm assuming you want to know what's the error on the validation or the test set. So that's straightforward. No, you will run your learned program or your ML model.
Yes, sir. In the theoretically, they represent that expected error as and some symbolic notations they used to represent in the textual. Similar to that, practically, when we apply a data set, after we split it, training, validation, testing, we are executing the model. After it learns, it gives some outcome. So
Correct.
the outcome, how it will be, whether it will be as an our expected outcome, or along with that, we'll get some errors also.
You will, I mean, generally speaking, you will get errors also, right? But what will be your error rate? That there's no way to quantify it mathematically, at least. At least not that I know of. You know. So for simple models, I mean, for linear models, there are you can get a lot more information from the model, but that's the end of it. Because see, to know the error rate, you might be able to prove some bounds on the error rate, but otherwise, what is the true error rate and all? Because you need to know the actual error. That again, you don't have with you, right? So you will not be able to get that that for I guess many ML algorithms, as far as I know. Yeah.
Okay, sir. Is there is any constraint to have number of data set to segregate into training validation? That is just like 100 record sets or 1,000. Is there is any minimum ranges necessary for an ML model?
No, there's no necessity as such, but the idea is that as the model becomes more, let's say, complex, you will need more data to be able to learn the right function. Right in the sense, again, best approximate function. I mean, and we'll go through, how to understand things like complexity and all of that in the upcoming lectures, upcoming weeks. But there is no hard and fast rule. It's possible that for a simple model, even 100 examples may not be good enough. Or it's possible that for a complex model with the right initialization and all of many different bells and whistles, you might be able to do well within the first 100 examples itself. So I mean, it's there is no hard and fast rule, nor there is a very good rule of thumb also that exists here. So I mean, this is something that you'll have to go through rather painfully through experiments.
Okay, sir. can we able to proceed the data mining algorithm in ML model?
So ML model is sort of data mining though, right? You're trying to understand patterns
Yeah,
in.
when we are going for clustering or decision making, the algorithm what we have in your data mining concepts, we can implement here. In
So,
which way it differs?
so what is
ML?
data mining concepts? Because you'll have to be a bit more specific here.
No, we are mining the knowledge from that concept on it in data mining. In machine learning, how that algorithm differs.
So again, I guess the terminology may be a bit different, but I guess the idea is the same. So the point is you want to uncover patterns in the data at the end of the day. So knowledge in the sense is basically you want to understand what exists in the data, right? ML or ML algorithms are, I guess, one way of doing that. There are other, simple models. Different models that can do the same problem. So I would say, in some sense, ML models are mining data in this rough sense. Again, we can quibble over the terminology a bit, but that's how at least I understand machine learning to be.
Okay, sir. Thank you.
Yeah. What was in the chat? So where were we actually? So yeah, no, Jitendra, your question basically, yeah. So we cannot understand what's the minimum length of the data set to ensure 90% accuracy. That's not a question that anybody can answer for that, for now at least. Difference between validation and generalization. So validation is a subset of the data set that you already have. That's validation set that you call. Generalization is basically the point here is that you want to understand whether your model is able to perform well on unseen examples. Unseen in the sense something that hasn't been used by the model to train itself. So we use a validation set to understand generalization, right? So and how do we measure generalization? It's again using error metrics and stuff like that. So low error or high accuracy gives you better generalization. Could you explain the terminologies instance, space, and concept? I guess these are some specific terms. Let me just go through it. Okay, so instance space is basically your feature space, right? Now, for example, let's say I have a feature which tells you let's say in this example, the image example, right? The cat and dog example. So I have, for example, let's say a 32 by 32 pixel image, right? And let's say it's grayscale for now. So the instance space here is basically all the possible values that can exist in this particular image space. So I have 32 cross 32, there is 1024 pixels, and each of them can take a value between 0 to 1, right? Because that's the grayscale, one way of representing grayscale values. So what ends up happening is you have mathematically, if you want to represent it, it's something like this, right? You will say it as a value between 0 to 1, close interval, right? Any value between 0 to 1, power 1024, right? So this is your instance space, right? So that's your space of your input data that can exist. Now, concept is basically a subset of this. Now, there'll be so many values in this particular instance space which don't correspond to cat or a dog, even for the matter, even an animal, right? So rather, now here the point is that subset of this particular all possible values which correspond to a cat or correspond to a dog, that becomes a concept. So we were trying to learn in this instance space, which is a huge space. We want to learn this concept related mapping. So I have some set of examples which can be mapped to cat and dog. only for those I want to be able to find the right function in some sense. That's how you could understand instance space and concept. Can you solve some assignments of previous example in this way? You will get percent. Okay, so previous years assignment, if I have to solve, it's all very in some sense a more general English sort of questions only. So what is meant by overfitting? What is meant by this one? From next class, I think so we'll do more like involved sort of math sort of assignments, right? So Isan, I guess that's the answer I have for you. Assignment one solution. So I guess just the next day. So I guess Wednesday is your assignment one submission date, right? So just the next day you'll be given the solution. How to decrease time complexity for a very large data set? So time complexity. So Varun, so time complexity in the sense of what, the training time or the testing time? There are two very different things. So if you want to clarify that, I can give the right things in that sense. Where and when the normalization comes into the picture? Okay, fine. Was normalization covered though? Okay, so normalization. See, many ML algorithms that you will go through actually ends up getting affected by what the range of different features that you're using, right? Now, for example, let's say if I have age, for example, as one of the features for some problem statement that you're trying to solve, right? I can mention age in years. I can mention age in months, right? I can mention age, the same age in decades, right? And so on. So what ends up happening is, for example, let's say if you have age and let's say height, right? Two features that you have with you for some prediction problem that you're trying to do. Now, because again, height also can be measured either in centimeters, inches, and so on. So the problem is, let's say if I mention age in months, right? So let's say a 20-year-old person will have 20 into 12, right? So 240 as its value, and his height is, for example, let's say 5'6". So you'll say 5.5 is your input to your ML model. Now, the problem, some ML models have this problem, is that if your feature, if two features are different in their ranges, right? The model starts becoming more and more sensitive to one which has a higher range or very wide range of values, right? Now, because height is generally constrained, you will have maximum, let's say, if you take feet or I mean, inches or whatever, you'll have like 0 to 6, let's say 7, Amitabh Bachchan, let's say, for example, right? So that's what you will have. But age in months can go to a very large number. So what we try to do is we try to make different features come on the same scale as each other, so that the model is not biased by any single feature. Rather, it tries to treat every feature in the same way and thus learn a better function. That's the idea behind normalization. Can you tell or share a few dataset linked to TriML for computer vision to practice a concept which will learn? Okay, so Kaggle as a platform, again, I have used this a lot. So Kaggle platform as such is a very good platform. You can go ahead and you have open source data sets. They also have compute power for you. They have support for many different Python libraries. So pick your favorite library, pick your favorite data set. You can work there without any issues. Yeah. Explain overfitting and underfitting and how they can be adjusted with bias and variance. So you don't adjust underfitting, overfitting with bias and variance. So okay, so the idea is overfitting is again we'll do this right now just over English, but when we get to the math, it will become more clear. So overfitting is basically you're doing well on the training set and not doing well on the testing on the validation set, right? That is basically we're saying that again going back to the student example, right? So where he can memorize and not learn the right concepts or whatever. So that's a student who has memorized everything but not doing well on the generalization, that is on your unseen questions or unseen examples. So that generally happens because you have low bias but high variance, right? Now, why is that, and everything will come to in the coming weeks, right? But that's the idea. So if you see a model, if you see a model having very good training, error, very low training error, but very high testing error or validation error, it it means it has low bias but high variance, right? And underfitting is basically it's not able to do well on the training set itself, right? It's not even able to memorize the data also, right? That is called as an underfitting problem. So that is basically generally when you have high bias, but and possibly low variance, right? So then what you do is you have again very standard ways of solving these problems exist. One very straightforward one very best solution is get more training examples, but generally that's not possible. uh, Again, think of medical domain and stuff like that, where for example you're trying to figure out whether a particular person has autism or not, right? You will not have enough people who have autism in the first place, right? And that who are willing to give you their medical records, right? That's even a smaller number. So generally that's not possible. So rather what you will end up doing is you'll try to solve this problem in a different way. So if you want to reduce the bias, you want to go towards simpler models. If you want to reduce variance, sorry, you want to reduce the bias, you will go to complex models. You want to reduce the variance, you go towards simpler models. Now that's the trade-off that comes in, right? Because both of them, they want to solve problems in different way. You will have to choose the best one, and the end all be all goal is validation error. If that's good enough, you take that at its face value and move ahead. So Boolean functions are basically just your a function which takes Boolean inputs and gives a Boolean output. That's a Boolean function. Um, I mean, so because so one interesting thing about Boolean functions is that you can clearly understand how many number of possible values, possible functions can exist, right? Whereas in, for example, let's say if a feature is real value, because real numbers are infinite in nature, right? So you will not you don't have a handle on what number that will be. Boolean functions don't I mean have that property that you can clearly understand how many they will be. But the issue is once you have many, then you still cannot solve the problem in polynomial time, and that's the issue there. Training.
Sir, it's regarding time complexity. Hello. Hello.
Oh, yeah. Okay. Got it. Yeah.
So say you have very large data and I want to do for training set and all. So how does it like best time complexity? So the reduce the time for the output, and that's what I want. How to reduce out? It's a very huge data.
Right. So again, at least what I have seen is training time. Generally, if you want to reduce, you will either want to go for a simpler model because you have less number of parameters to deal with. So your model becomes. I mean, you can get to different iterations faster. That's one way. Other ways, for example, using higher compute power. So again, I would I mean, I understand that this is an issue, but training time reduction, I would not worry too much about it, right? Uh, so some standard ways are basically getting high compute power and stuff like that. The testing time, testing time complexity, that reduction is a big thing, because let's say, for example, if you want to ship your model to a low end phone, for example, right? Like a Siri sort of thing. So then yes, then you need to worry about testing, timing, as how much time it takes for your model to run, not train but just run. So that I would say it's a software engineering plus ML problem. Again, I don't have much experience on that, so I might not be the right person to give you any advice on that. Yes, Abhirup, if you have anything to.
Yeah. So there is something called dimensionality reduction, basically, for the feature set, that actually helps in reducing the number of hours required to train the model. Basically, we kick out feature sets which we have taken as input. Uh, there is something called that. Like, I studied long time back, so I don't remember, but there is something called dimensionality reduction where particular feature sets plays the biggest role to actually determine the correct prediction.
Right. So, so it basically falls under the idea of reducing the number of parameters.
Yes, feature set.
End of the
Feature.
day, right. So at the end of the day, dimensional reduction will help you reduce the number of features. So when that happens, the number of parameters will reduce at proportionally or whatever, right? So hence, so that basically reduces your number of, let's say, if you're using a neural network, then the number of updates that you have to do for every different parameters. Hence, your training time can reduce. Yeah, Varun. I hope that answers your question.
Yeah, thanks.
Right. Any ethical moral code issue regarding sharing old assignments? Does NPTEL allow partners to share the old assignments with or without answers? So at least for this particular course, I guess they have different assignments every year. So again, I'll have to ask and get back to you, Balaji. 10,000 emails in the 200 are spam. Model 150 are spam, out of which 50 is actually spam. This is model's prediction and recall. Can you please solve this one? Is this a problem of the current assignment? So then I cannot solve it. I mean, you'll have to solve it, and we can discuss the solution in the next meet as such, right? So hopefully the what I mentioned, the example now should be enough to solve this problem, or go ahead and see the lectures once again. Yeah. Can we use features and parameters interchangeably? You mean the terms? Bharat? No. So features are basically the input to the model, right? So here, for example, when I have this image, for example, cat and dog example, the feature is basically each pixel's value that is there. Right. So that's the feature of the input. The parameter is basically all the probably the weights or the decision rules, for example, which the model has learned as part of its training regime, right? Those are called as parameters, right? So no, they're not interchangeable, but yes, your output depends on both of them, right? At the end, what features you use and what parameters have been learned or are learning, that's the I mean, the model depends on both of them. Reducing the number of parameters of number of features of parameters means reducing the bias. So if you reduce the number of features, again, the issue here is, for example, it may be a feature which is very important, so you will then again not be able to learn the model well, which means you're increasing the bias, right? Number of parameters, generally yes, because the more parameters you have, it means the model is more complex. So it will be able to handle simple relations, which means you'll have low bias, right? But more parameters means more complex, so more variance, and that's the trade-off that you will end up going into this. It's like picking up features that actually has biggest impact on accuracy of the model. Nothing to do with this.
You can skip it. It's just that I responding to that dimensionality reduction.
Right.
to set.
Okay, fine. Good. Okay. So parameters are a subset of features. Would it be correct? No. Again, so Varad, see, uh, uh, features and parameters are completely different. So, okay, in the example that I gave you, the initial example that we saw, the function f of x equal to beta naught plus beta 1x, right? So x is the feature because that is what describes the input, right? So features are basically which describe the input. Parameters are basically what all values that the model has learned or will learn to get to that particular output, right? So here beta naught and beta 1 are the parameters of the model. So what you want to do is you have x's and you have the actual y's that you have in your training set and learn the parameters. So parameters are learned using features and output, right? And once you have learned those parameters, the output is then calculated taking the features and the parameters. Mm. Uh, you told about autism detection. If you're not having enough data set in our hand, how to start with simple model? Can we just tell once again? Yeah. Okay. So not having enough data is a very standard problem in machine learning. Again, so as Avirup mentioned, the dimensional reduction is one such things where one such method where what we do is we try to reduce the number of features that the model will see, and therefore reduce the number of parameters that the model will see. Hopefully, learn enough from that, right? So again, and this is also where domain knowledge becomes important, right? So having the idea of what autism could be, or what are good markers of autism detection. So you can talk to, for example, neural biologists and neural surgeons and people who work in this field, and try to understand what could be other markers either from the brain or from the behavior, etc. So try to augment your data, right? That's what you can do. So if there's not enough data, then you don't have anything else. You cannot do anything else, right? Um, there are other different ways of solving it. For example, again, so something like um, what you do is one possible way of solving this could be, for example, let's say you take healthy data, like I mean people who don't have autism, take all their data and try to learn some sort of unsupervised sort of a learning algorithm, and then see how much that differs from when I give autism data as input, right? So that is one other way of looking at things. So there are different ways to solve this problem, but this is a problem which is rampant in ML community. You will never have enough data to do stuff that you want to do, right? But there are ways to solve it. Again, they may not always work, but again, rules of thumb that you can try and see if it works for your data set. That's how it's going to be. Yeah. Any other questions? What causes the bias and how do we remove it? Okay. So bias is basically caused by the fact that the model does not have enough power to learn simple relations. And again, when we do the math, it'll become much more clearer why it is that way, and what can we do to remove it and all. So I would say hold off on that particular point. Probably in the coming week, we'll have much more detailed and much more clear clarification of what it means and everything. Yeah. Example of hypothesis space and hypothesis, where M and C are elements of R, and hypothesis H is one function with any value of MNC. That's correct. Yeah. So hypothesis space is basically all possible, function forms, all possible functions of a given form or whatever. And a hypothesis, a single hypothesis, is that one particular function that you pick. So yes, both M and C, when you choose, that becomes one particular hypothesis, and all possible such functions are called hypothesis, the hypothesis space. Uh, You mean clustering of data for persons not having autism under unsupervised learning? I wouldn't say clustering. This goes into something called as self-supervised learning, not semi-supervised. Again, what ma'am has mentioned, self-supervised learning. It's a bit different from clustering. Hopefully, when we go to clustering or unsupervised learning, I'll if possible, I'll go into a bit more detail there. Very interesting problem, very interesting problem space of ML as such. So we can see once we go there.
Sir, the question is regarding these parameters which you explained just now.
Sure.
Say we have a training sample and there are already so many algorithms which is already available. So
Right.
I just apply this training data to the algorithm existing. It could be Bayesian or neural network. And then when I do this, can I restrict on the number of parameters I need? Can I do, sir? This is a question actually.
Yeah, you can. You can do that. So at least for neural networks, you have complete freedom of how many parameters you want to use or not want to use, right? And even for a given, for example, set of let's say number of parameters, if you want to give some sort of an ordering, and that was also discussed in the inductive bias thing, right? So where you want to say that, okay, very high values I do not want, I want low values and those sort of thing. So all that can be done in networks at least. Yeah, so it's possible to do that. Yeah.
Okay, sir. Thank you.
Yeah. Any other questions? So people who are planning to use this ML in your field of work, for example, let's say if you're from machine learning background or sorry, of a mechanical engineering background or civil engineering background. So if you have any specific questions to that also, I guess you can ask in the discussion forum also. But it would be interesting to hear any use cases that you guys think of where ML can help, where you plan to use ML in your work.
You mentioned about this discussion forum. Is there any group in the WhatsApp kind of thing? I mean, I'm not aware.
No. No. So there's no WhatsApp group. There's only the Google group that exists.
Google group is what? I mean, any link can you just put in the chat?
So you have the ask a question, tag this one, right?
Oh, in the okay.
The course web in the course page, in the course web page. That's so you click that, you go to the Google group that I'm mentioning.
That's on the chat basis, right?
Right. Yes.
Okay.
Sir, when we will be getting this problem on this bias and variance, sir, the numerical numbering? I guess when the algorithm is taught to us, probably.
Yes. I think it should come in. I guess week 2 or maybe week 2. I guess we'll start because we'll start with linear regression and that's the best time to learn this bias variance sort of thing. I guess it'll be taught then. Otherwise, it'll be taught in the when dealing with hypothesis space and sorry, this learning dimension and all of that will come in the later part of the course. Yeah.
Okay.
Yeah.
Sir, I'm from mechanical background.
Yeah.
I wish to apply make a machine learning in the field, say optimizing some welding process. So I have some parameters like welding current, voltage, etc. So what set of that parameters would give me the best result in some kind of outputs like uh, its deposition, penetration, strength, etc. Or these kind of similar problems are there in other manufacturing processes like metal cutting, turning, and casting processes. So, how these machine learning algorithms will help me, or what kind of things that some kind of queries or some kind of guessing I have. And that is my
Okay. So yeah. So basically, you want to be able to optimize some part of your manufacturing process, right? Uh,
yes, sir, yes.
Right, and then so obviously, so that's where the the first two lectures of this week will become useful for you to frame the problem much better. So, for example, let's say, what do you want as your ML model to do, right? For example, let's say, is it some sort of optimizing, I guess. So one thing that I can think of is, let's say you want to reduce the wastage that you have in your manufacturing process, right? So then one way is, for example, let's say given a set of parameters, the parameters again could be, features could be, for example, let's say the uh, the the quality of the material that's going in, or the quality of the 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 machining process and stuff like that. So so basically you'll have to figure out what describes your input to the model, right? So what all can have an effect on this wastage process. You use that, and then you try to predict what will be the wastage if this sort of things happen, right? And then basically so use this as a so have data which can give you, which has sort of mapping with you, and use that to optimize your learning, your manufacturing process. So for example, let's say your ML model could end up telling you, okay, um, a large I mean, hopefully the low quality of your a machine is giving you large wastage, which makes sense intuitively. But now you have a way to quantify it also, right? Because all those parameters which are connecting your your that feature of quality of your machine to your wastage, you now have a way to quantify that effect. So you can use that to then go back to your drawing board and see, okay, what can we do next? What can we how can we improve this particular this particular part of the manufacturing process? So I guess, so these are some real applications of ML. Are there applications of ML in cybersecurity? Yes, actually, there are. I am again unaware of that particular field altogether. But yes, I do see now and then some people, working in that field with ML. So it's a pretty exciting field. So, but and there is, so you can just look at what people do currently with that, and hopefully you'll get an idea as to how people are trying to use it in that field, and go ahead, right? Are we supposed to participate in one problem session every week, or all of them? So I would suggest try to attend all of them, because different people will have different, they'll try to cover different parts of the lectures. That's point number one. Point number two, a same problem, for example, let's say bias versus variance, for example, right? My way of telling may be different from somebody else. So hopefully that helps. And in case if you're not able to make it to each of the live sessions, you can always watch the recordings. And in case you have doubts in the recordings, you can always contact us on the discussion forum. uh, okay, since please give me some so again, suggestions to start my journey in machine learning. Just a moment, I'll get my charger, just a moment. Suggestions to start my journey in machine learning. So yeah, this course is a good starting point. For hands-on experience, yes. So I would suggest Kaggle again. A personal suggestion that Kaggle has a lot of compute power, has variety of data sets, which you can find interesting. For example, if you want to do like a image-based data set or a sequence-based data set, for example, text, audio, etc. So you can try that out. Recordings links will be sent to you by the NPTEL announcements. So I'll just remind them that to share them with you. Yes. Go ahead.
Sir, I have a
Hello, sir.
sir.
Yeah, this Google data set, whatever the data set is available, it is a pre-processed one. Is it pre-processed one, or we need to do the pre-processing also in that? Hello, can you hear me?
Yeah, I can hear you. Which data
Yeah.
set you're talking about?
No, whatever the data set we are getting from the net, online source, whether it is a pre-processed one or we need to do the pre-processing there.
So you get both versions. Kaggle again has again both versions of many data sets. And they'll simply mention, so is it pre-processed or not, and what kind of pre-processing has been done, because that will, uh, can you mute yourself?
Yeah.
Yeah. So they'll mention, what kind of pre-processing has been done also, because that can have an effect on your this one, outputs and stuff like that. Um, so again, just read through, the what data set it is, and so on. Yeah. So that should have the details. Yes, Subhajit, go ahead.
Yeah, can you once show in future lecture itself that how in hands-on training on how Kaggle or Google Colab or Scikit-learn these kind of websites can be used for applying machine learning for our own data or like that.
Okay, sure. So we can have a coding round sort of a thing. So where I can probably explain some things around how to go about coding in these general platforms and stuff like that. So we can do that, no problem. We will see which week it sets better. Yeah, so we can do that, no problem. Can we use ML for the field of biosensors to examine data for incorrect results, either positive or negative? Yes, that's a very good field. So I mean, this basically goes into medical domain sort of issues also. So people have been trying to use ML to, again, it's not to replace doctors, that we haven't reached that level yet, but it's more about to give like a first sort of impression, right? So what, and to also help the doctor in some sense that, instead of going through like a huge chunk of data about you, they can also have like a first impression and work off of there. So yes, it's actually a very up and coming field. Do we have programming assignments? So again, I'm not really sure about the about this part. Let me just check the previous. So actually, you can do one thing. You can just mention this question on the discussion forum. The course TAs will be able to answer this question better. How to submit the assignments whenever they give. I mean, you just need to answer your multiple choice or whatever the format is. And just click submit. I guess I don't know why. What's the complexity there, Dheeraj?
I have one question. For the assignment, there is one was posted where the answers are given.
Which answers
It's
are given?
not the assignment one that is having a MCQ. All
Okay.
the replies are also given. So I thought it will be an assignment for the testing, or it is just for the understanding that, because answers are given. That's what I'm saying. The first assignment what has come.
Where have they given the answers? I
That
don't.
is assignment 0 actually. That is for showing how assignments will come.
Yeah, that is assignment 0. Yeah.
Yeah, so the assignment 1 is basically yeah, so that's due on this Wednesday, right?
Okay.
For
Okay.
that,
It has not yet to come. Sorry. Sorry. Okay. Okay.
yeah, yeah,
So I was confused. It's not there.
right. Mm, okay. Any other questions as such, if you have? So I guess I hope the idea between the training, validation, and testing set is clear. That will become very useful when you start, uh, going into the next lectures and into your practice sessions when you want to implement algorithms. How difficult question can come in exam? Again, there's no way to reliably quantify this. This itself is a machine learning problem. So I would suggest you to uh, give your best. Uh, will we do some projects using machine learning in the exam? No, no. The exam will not have any project doing as such, at least as far as I understand it. Again, things about this exam assignments, I would encourage you to ask on the discussion forum. The course TS will be able to answer you better. Yeah. Um, how do we start applying whatever we learn practically, since this course is meant to be theoretical one? Right. So as you know, I guess Subhajit mentioned, so we can have a problems or a coding sort of a session. Either me or one of the other two TS, PMRF TS can take it up, and we'll show you, how different things you can do. So I would suggest, next week, at least is also the week two lecture, week two content is on, simple algorithms like linear regression and stuff like that. So what we can do is we can show you how to use it for example, let's say Kaggle or Google Colab, notebook sort of a thing. Yeah. What are the prerequisites to learn machine learning from scratch? Um, So prerequisites, I would say again. Whatever basics is necessary, ma'am will do in the course anyway. If you want to do something more than that, then yes, things like optimization theory, that is a very good, resource to have with you, a good prerequisite to have with you. There are things like, for example, um, uh, having a strong knowledge of probability, linear algebra, all of these are, good things to have in your bucket. Uh, Sources available to get other than Kaggle. So again, other than Kaggle, so I don't remember, but yes, there are um, many other. It's one sort of equal to Kaggle. Um, and again, see, there are possibilities that, I'm sorry.
Kaggle is here.
Right. Yes, yes.
Just type in the Google, you get it.
That's right. So other than Kaggle, again, so for example, there can be some very specialized data sets that you might need. For example, let's say if you want to work on something like a brain related data set, right? Kaggle may not have it. So then you'll have to do you have to search respective domain lab people who work on something like that, right? So for example, let's say if you want to learn about the brain state using the fMRI recordings. So again, Kaggle may not have that sort of specialized data sets as such. For that, you'll have to go through other sources, different labs around the world which work on similar problem statements, stuff like that. Why do we say for overfitting bias? Again, I would say just hold off. Oh, sorry, overfitting bias is not high. Overfitting bias is low. Again, I would say just hold off on for a while. We'll do the bias variance trade off well in the coming weeks. Yes. So okay. So these interactive sessions will happen once a week, every week for the coming for the duration of your course. That's 8 weeks, right? So we'll have 8 such sessions. Each TA will do the 8 such sessions, and for my session, this timing is fixed, so it will always be on Saturdays, 4 to 6.
Sir, I have just one question, which is
Yeah.
always puzzling me. How many times I read on the internet and get confused. That
Sure.
is, there is most important question is in Bayesian learning that we always say likelihood estimate and probability. I always confuse these two terms. We use likelihood and probability. In fact, I've been reading on the net so many things, but I'm still not getting. Can you tell me very intuitively way to just differentiate these two?
Okay, good enough. So this actually has the roots in machine learning inspired from statistics. So okay, so I'll give you the required background to understand this, why you need to think of it this way. So let's say you have your data set, right? That's your X and Y. Let's say we're dealing with a supervised learning problem, right? X and Y. So X is all your features, and this is your, let's say, classification or whatever, some target, some output that you want to generate, right? Now, in statistical machine learning, what we do is we actually treat them not as just usual variables, but as actually a random variable, right? Now, when you have a random variable, it means you have a probability distribution for it, right? And then we make some other assumptions. I'll not go into the math for now, but let's say the assumption is that X follows some distribution, right? So X follows some distribution. More importantly, X and Y have a joint distribution, P of X and XY, right? So now, what you want to do rather is you want to see what is the right target given a particular X, right? Because you want to predict that, you want to learn that function, you want to go from X to Y, right? So ideally what you want is you want to find something like this, Y given X, right? So for a given X, what is the probability for Y to be some value, right? So what is the distribution of Y for a given X? So that is again the cat dog example. Let's take it. So X is the image. What is the probability that it belongs to the class cat? What is the probability it belongs to the class dog? Right now, using the great Bayesian theorem, you can just write it as X given Y into probability of Y by probability of X, right? So this is termed as likelihood, because what it is saying, it is saying how likely is this particular X belonging to this class, right? So if I give a dog image and my Y, for example, is, let's say, cat, the probability that the dog image belongs to this class, this cat class, is very low. We generally don't take zeros in these discussions, but let's take very low, right? 10 to the power minus.
Can you kindly little more? I mean, that's not very distinct on the right hand side. Can you please make it a little more distinct? I mean,
Sorry,
cannot
what is
read it.
the math is
We
not
have written, yeah, just cannot read it. I mean, or just to follow.
right.
Little more distinct. Maybe the chalk has a problem.
Yeah, fine. So So y given x, is this hopefully x given y into probability of y by probability of x. Right? This is what I'm talking about. So this is termed as likelihood. So what we're saying how likely is this particular value x that we have seen, that is the image in our case, belong to this particular class, right? And probability of y is again termed as prior. So basically, without any information about x, like you don't have any x with you, what's the general likelihood, general possibility of any image belonging to a cat or a dog class. We generally take this equal priors and unless you want to bias your decisions, etc. And probability of x, this is something that again tells you what is the probability of getting an image like this in the first place, right? Again, that's because, for example, as I mentioned in the inductive, sorry, the what is it called, that uh, inductive space in the concept, you know. Uh, uh, things there. So the idea is that X can be any image, any image which has, let's say, 1024, dimensions of a grayscale, right? So now, obviously, the probability of seeing, for example, let's say everything black or everything white, that probability is very low, right? Because such images are not generally cats or dogs, right? So that way. So now then what we say this to be posterior because we have now updated our belief about the class and all of that. This is called likelihood. Okay. So the idea is how likely is the value that I have for a given particular class that I have with me. This is the most upper level I can give you what you can say intuition into this. Does that help, Krishna?
Yeah, I got it, sir. So where I'm coming from is, if you
Yeah.
look purely from a probability or mathematician's perspective, both
Right.
the probability of y given an x, probability of x given y, both are conditional probabilities. But
Correct.
in machine learning, we interpret that probability of x given y as a likelihood. But actually, mathematically, both are conditional probabilities, right?
Yes, correct. That is true. So both are conditional probabilities. That is true. The issue, so why we want to interpret them differently is because of this fact that we actually want to find what the right y is for a given x, right? So we have x with us. We have the let's say the test data in the ML parlance, right? So we have the test data. We want to find what the y is. So what we'll do is we'll say, okay, I will find out how likely is this test data for a given y, and then try to reason from there. That's the thought process.
Yes, I got it. I got it, sir. Thank you.
Yeah. Okay. Right. Any other question? Okay. Sorry if you have yeah. So okay, recordings will come by the NPTEL announcements, probably in the coming week. Yeah. I can ask them once and figure out what's the exact timing. Can you explain inductive bias, inductive learning? So, okay. So inductive bias is the choice that we make upon the hypothesis space, right? For example, again, as you mentioned, right? Choosing linear functions. So y equal to, sorry, f of x equal to beta naught plus beta 1x is a choice we're making that that the data set follows in this, in this form. So that's the bias that's coming in. Inductive learning is basically learning through examples, right? So, and that's exactly what we're doing in training an ML model, right? So we say, okay, these are the features, these are the corresponding outputs. So now you have examples of your the right mappings with you. You will now tell the model, okay, this is what you need to learn. You have to learn a mapping from X to Y. So if anywhere it becomes wrong, we say, okay, this is not the right answer. this is the right answer. So change your mapping, whatever you have, to give me the right answer. That's called inductive learning. So learning through examples. That's the big picture in some sense. Yeah. Okay. Any other questions? Do we need to have strong knowledge of probabilities because started to ML? No, I mean, I would say, see, because probability statistics, they are a whole field in themselves, right? But what you will require for ML, that you will not be able to know before you learn ML. So I would say start with this course and see wherever you're feeling a bit off, or something that you don't understand clearly. Feel free to ask it during the live sessions or in the course forum. We can either point you to the right resource, or if it is something that will benefit the large group of you, we can even have a discussion on that in the live session. That's not a problem. Yeah. Because stats deals with a lot of different stuff. Probability again has very different, parts in it. Not all of that may be required for you to learn ML efficiently. So I would say, start with this course. Let's see, if you feel something is off, you can ask us. Yeah. Any other questions? So I understand that the first week is going to be like this. In the second week, I guess we have a lot of stuff to cover. So we'll have decision trees, we'll have linear regression, and overfitting is discussed in more detail in the next upcoming lecture, upcoming week. So we'll have a lot of math to work with, and we can discuss in more details at that time.
Sir, just to summarize, by understanding of whole machine learning is
Sure.
all about finding probability of y given x, right?
Yes.
Summarize that. Okay.
Correct.
So that is a Bayesian way of learning. Okay. So how do we derive that probability of y given x? By data, by getting more and more data, so that prediction improves, probability of y given x improves as you get more and more data.
Correct.
Yeah. So that is Bayesian learning. Okay. So
Yeah.
But
this is.
Yeah. Are there any other ways of learning? So one is normal statistical regression we do, which we do in our college days, right? High school days. Okay, that is linear regression. We easily understand that is reducing the sum of the square differences and then finding out the coefficients, and that is a linear regression. Actually, Bayesian doesn't come there. So Bayesian comes when there are. Bayesian is another approach, right? Another approach towards learning than statistical.
So I would argue that Bayesian is also in linear regression, though, right? Because so why does it come in that way? Is because we are assuming a functional form between x and y, and then we are asking the question, okay, given this functional form, give me the best y. That's the thing that we're trying to answer. So that way you can look at almost a lot of ML in this Bayesian framework, saying, okay, we'll assume a functional form, and now give me what is the best probability, or the best y or whatever.
Yeah, sir, but without modeling it as a function, as a polynomial or something, purely by Bayesian way, by looking at the data, we can always derive the probability distributions, right? Even though the computations may be high, probability of y of x can always be derived, no matter what. Okay, what kind of model it is, linear, non-linear, doesn't matter.
So true. I mean, given infinite computation time, given infinite computation power, you can always compute that. The issue lies in the P of X actually, because P of X is not an easy thing to compute. P of X means you need to look at all possible X, all possible Y, and all of that. Take a marginal over this joint distribution. That's not an easy thing to do. And that's where we sort of bring this inductive bias into it, because to be able to bring the problem into a solvable solution, something that can be solved in a finite amount of time, for sorry, not finite, I mean in computationally tractable form. We bring this assumptions, more assumptions into this into the problem statement. That's one. Second thing is, these sort of systems, uh, when you apply for large dimensional data sets, right? So P of X, for example, if X is an image, and if I take, for example, an image that we get today in today's phones, that dimensionality is just way too high to even get a good probability estimate in the first place. So you will not be able to even get a reliable probability model out of it. That's another problem. So even if you could do it, you will not. This estimate will be very off, just for the fact that it's a high dimensional data set, and getting a probability estimate on high dimensional data set is difficult.
Okay. Okay, sir. I got it. I got it. Thank you.
Yeah. And one more point I would like to add is, so this is basically just supervised learning, supervised machine learning. When you have Y and X and right, when you bring in unsupervised, so it's just X. There's just P of X there with you, right? So there we are asking a sort of a different question also into it, and the way we model it is again different, and all of that is a different problem statement. And I guess we'll deal with clustering in this course. So we'll see a very interesting mapping between how clustering can be seen as a probability distribution, and what do we do there, which relates this probability and the algorithm that you have learned in some sense. So that is what's going to give that mapping for you, right? And then when you bring in again reinforcement learning, that yes, it does. You can always use a probability model to explain, I mean mathematically describe it, but at the end of the day, yes, it becomes computationally challenging to be able to solve the problem, right? So that's the relation that we have. I see 3 sessions, 31st, 29th, and August 1st. Is everything same or different? Again, so I mentioned this before that not all of us will do the same stuff every week. It's possible that we'll have very distinct, parts that we cover, or it can be like a same problem, but looking at different views of the problem, right? So I would suggest attending all of them. If you can't, there's always recordings, and you can always, post questions for each of our sessions in the discussion group. Plus, my session also has this Q&A sort of a thing, so you can put your questions there also. There are 2 more sessions. Yeah, just now I answered that it can be different, it can be same. Again, this first week, so we're still trying to figure out some details, but it's likely that things will change when we go into more, next upcoming weeks. Yeah. Okay. Any other doubts?
Hello. Hello.
Yeah, go ahead. Who is it?
Yeah. See, as far as my understanding, this underfitting also we have a problem, right? High bias and variance, and overfitting also creating issues, right? With respect to bias and variance. So always bias and variance trade-off is there, right? So how to overcome this problem? That is some kind of proper fitting. How do we achieve that?
Yeah. So correct. I mean, um, so we basically, yes, we want so-called proper fitting of the data, but it's possible that you may not always have it, right? Again, I guess this has been discussed by ma'am also in her lectures, that there are many different errors that can creep in your learning algorithm, right? For example, inductive bias is one such issue, right? Limited data is another issue, and stuff like that. So I mean, so what we try to do at the end of the day is we don't want either of this, overfitting or underfitting, and what we and it's more like a judgment call sort of a thing, right? So at the end of the day, when you look at your loss curves and all of that, what you want is basically something which has uh, acceptable amount of validation error, acceptable amount of training error. That is what you will choose as your best model, right? Now acceptability can be very different for different problem statements. That's something that you will have to get by practice, or see how people have solved the similar problem in the field, and you can get a good estimate of what can you expect the ML model to do, and from there you need to work this out. Um, uh, but yes, we have, I mean, this is a well-researched problem, that if you have overfitting, what can you do to to reduce your variance? If you have underfitting, what can you do to reduce your bias and stuff like that? But yes, you will not be able to, nail it down. You'll not be able to get perfect prediction, right? And multiple reasons exist which are out of your control. Right? So that's the error that you will have to live with, in some sense. Why you have to intro to ML courses, Sudeshna ma'am and Balram. Huh. I don't know. I mean, both of them wanted to give a course, so they have given. One is an 8 week. So one thing is Sudeshna ma'am's is 8 week course. Balram sir's is 12-week course. So you can look at the course content and choose one if you're conflicted about it, right? So I have been a TA for the Balraman sir's course already once, and they do fair amount of math there, and I guess Sudeshna ma'am's also is there. So your choice, right? So you can see what works for you. Right. Any other questions, or we can call this to an end? Um, okay, good enough. Thank you. Thank you. Thank you. Thank you. Recording of the session, yes. Again, I mean, you will get an announcement from NPTEL, which will have the links for the recordings of all the TA sessions or by all the TAs that happened over time. Yeah, um, that'll happen. Okay. Fine. So I guess next week there'll be linear regression. There'll be decision trees, and there's also some Python exercise on it. So we'll see, what has been used to, do that, and then we can do like a coding session also next week, and we'll also discuss the answers, questions, if any questions, if you have from the current week's assignment. Yeah. Um, uh, any question that was not clear, or the answer was not satisfactory or whatever, so we can discuss that also. Fine. Yeah. Thank you.
I just have one query that for the algorithms.
Yeah.
For the X set of data, all the inputs, all the features with the parameters, that is the parameters are the instances, right? All these parameters for the features. And Y is the target data. The machine learning will do the algorithm. The best fit algorithm, there will be a algorithm set which is to be chosen. Either it be a linear or non-linear, or maybe a Boolean kind of thing. So that what algorithm to be sought for for getting the target answer. So there is a little bit more, confusion of mine. So maybe silly question, but
So you're saying that we have multiple algorithms. How do we choose one? Is that?
yeah.
Huh. Yeah. So again, yeah. So we have multiple algorithms. That is true. But the point here is try to understand what are the assumptions behind each algorithm. Right. At the end of the day, every algorithm assumes something and then gives you a solution. Right. So, for example, in linear regression that you will do in the coming days, you assume a linear mapping. So the question then remains: is that assumption good enough for you? Are you okay to
Yes.
live with the assumption or not?
Yeah.
If you no, then yes, you have to go to a different algorithm and try your hand there. Uh, Again, each algorithm has its own issues also, right? For example, when you go with linear regression, you might be able to get answers very quickly compared to, let's say, neural networks, right? So each algorithm has its own assumptions and issues that exist. So you need to be okay with what assumptions it has, and are you okay to deal with the issues that exist in the algorithm. So that will be your choice at the end of the day. And also additionally, how well do you want to fit the training data, right? Simpler algorithms may not be able to do well, so you might have to, without any choice, even if you're not okay with the assumptions made in the other algorithm, you might want to go there and see how the accuracy is. So it's more like an exploration of all possible, many possible, answers that you have, and then you try to choose the best one that can explain your data. That's the current method. Yeah. So you will not have a pre-packaged sort of, okay, this data,
So the
this.
training will be given on how to choose the algorithms. So if there is a data set only for the words, say there's one thing madam has shown that day, that there is a training set, that location, author, where, at home or not, and then there is a question, then come to the to answer that how to find the data, that is Y value. So that
Right.
is from this there we have to work out that what algorithm it will fit in. It is basically the texts are given. So from there, what algorithm will be used? So there are many questions. I mean, not very clear on this. So there will be the training will be given, right, for this. How to choose
Yes.
the algorithm? What is the algorithm type?
Yeah, so as we go through the course, because I mean, a man will be teaching you different algorithms, what assumptions underlie them, and so on.
Right.
Will so yeah, so you will get a flavor on what things you'll probably be able to model from that particular algorithm from the particular data set. Now, uh, there's another issue which I feel you're hinting at is that it's possible that some data set may not be amenable to an algorithm, right? For example, let's say if you have text data,
Yeah.
how
So
do I
there are
use?
six
Yeah,
data there, and all of six features. But algorithm, the program is not really fitting in the six parameters. So in that case, what to do, kind of thing.
right. So you will get an idea about what algorithms can be, how to use different algorithms for different kind of data sets. And again, if that is not covered in the lectures, we're always here. For example, let's say tomorrow you want to ask, okay, how do I use this algorithm for this data set? We'll be able to, if not give you the right answer, at least guide you to what can be done for it. Yeah.
Okay. Right. Thank you, Raj, for this.
Sure.
All
Yeah.
the
No,
thank you.
yeah. No worries. Thank you. Learning will be excellent if we have access to previous year's assignments with or without answers. I greatly appreciate if you can help us to have access with them. Sure. Let me, contact NPTEL if that's possible. Um, and you know, uh, Actually go ahead and post it on the discussion forum. Again, this is something that is handled at the NPTEL level and at the course level. Um, we are here just to supplement what has been taught to that one. But fair question, I can raise it, push it along, and see what we can get out of it. Sure. Fine. If no further questions, I'll end the session for today. We'll meet again next Saturday, 4 p.m. Again, yeah, same link. And just to remind you, there's a Q&A session in this Teams link also. You also have the additional discussion forum. This Q&A, I'll be able to, answer everything right away. Discussion forum, whenever I look into it, which I do frequently. So if there's any question directed at me also, I can take it up there. Fine. Fine. Then we'll meet next Saturday. Yeah, 4 p.m. Thank you for attending this session and all the best.
Thank you.
Thank you.